Today we are going to be covering the module application of quantum physics, and we are starting with the topic nanophysics. So what is a nanomaterial? It is defined as a substance having size roughly 1 to 100 nanometers, and it has properties which vary with varying size, which is what is accountable for its high degree of controllability, and it is designed for increased strength and chemical reactivity. Now, which factors lead to it having such a high chemical reactivity? It is known as surface by volume ratio. As the material size reduces, the surface volume ratio increases, and since nanoparticles have larger surface area, the area by volume is higher for lower size, which increases the reactivity because of more surface atoms. Moving on to quantum confinement, if we reduce the size of the material from bulk size, electrons get confined to a region of the size of the material. At these confinement length scales, the electron energy levels are not continuous as in bulk, but are discrete because of confinement. Hence, quantum confinement is the spatial confinement of electron in one or more dimensions. As you can see, this is the graph for when there's no confinement in 1D, 2D and 3D. As we increase the confinement, we increase the signature of quantization of energy. There are three types of quantum confinements. 1D confinement is wherein electrons are confined in a single direction and are free to move in the other two directions. Here the density of states remains constant for a range of energy, and it suddenly increases with discrete amounts. For example, in graphene, MOS2 or WS2, and this 1D confinement is called quantum well. Now 2D confinement, which is also known as the quantum wire, wherein the particles are confined in two directions and free to move around the other one. And the energies are continuous in 1D and discrete in the other two. For example, in carbon nanotube and gold nanowire. 3D confinement is also known as the quantum pot, wherein the particles are confined in all three directions, so they cannot move about any direction. Energies are completely discrete, and density of states is a set of delta functions. For example, in gold nanoparticles, CDS, CDSC. Here, since the material size increases, the band gap also decreases. Properties of nanomaterials. First is the chemical properties. Reactivities of nanomaterials are more because of the high surface by volume ratio as seen in the graph. And as for thermal properties, the melting temperature decreases with size, because if the surface by volume ratio is small, the number of atoms on the surface increases. Optical properties. Absorption, transmission and reflection changes with size due to quantum confinement because of the band gap. Electrical resistivity or conductivity is pretty high for these type of materials. As for mechanical properties, smaller size leads to more imperfections. But since the nanomaterials are small, there are less imperfections in dislocation and vacancies.
What?
Magnetic properties do not vary if we change size of a bulk material, because number of magnetic domains doesn't change significantly. Non-ferro bulk materials exhibit ferromagnetic like behavior. For example, bulk gold is non-magnetic.